Today we're going to be looking at some more functions and their notation in particular so that we get used to the way that they're written and we are able to interpret what it really means. So again, we're dealing with the inputs, the outputs, the independent values, dependent variables. And when we're looking at these functions, you're going to see below this f of x or g of x or h of x kind of notation. We need to be able to understand what that means. So it says we're going to evaluate each of the following given the function definitions and their input values. So as you can see here on part A has the function f of x is equal to 5x minus 2. Now we may be used to seeing this as y is equal to 5x minus 2. It's the same kind of idea, it's just that with this function notation, this is saying anywhere I see an x, we're going to make it a 3. So I'm going to go into this first function and say, okay, here's an x, I'm going to make it a 3, and then I'm going to solve. So 5 times 3 is 15, minus 2, our final answer here is 13. So the function evaluated at 3 is equal to 13. Okay, same idea with negative 2. This function, anywhere I see an x, I make it a negative 2. So the function evaluated at negative 2, when I simplify this, is negative 2. Okay, it's the same thing for all of these. So g of x, now it's just a different function, same concept. Wherever I see an x, I'm going to make it a 3. So 3 squared is 9, plus 4, we get 13. Anywhere I see an x, I make it a 0. 0 squared is 0, plus 4, we get 4. So our two answers here, g of 3 is 13, the g function evaluated at 0 is 4. Okay, our last one we have is the h function. And we're going to plug in, same idea, anywhere I see an x, I make it a 3, so I see 2 cubed, that's like saying 2 times 2 times 2, which gives you 8. And now I have 2 to the negative 2. And so when we plug this in our calculator, it may give you 0.25, you can change it into a fraction. It will turn out to be 1. Okay, so don't confuse it with multiplication. You want to be careful. This is almost more we're saying like we're plugging it in. Think of plugging it in, that's your input. So this is going to be your final answer, okay? The x value, your input, I'm plugging the x value into the function. I'm going to get out my final answer, my final y value. Okay, so if we look at a table down here, we have something about boiling water. Boiling water at 212 degrees Fahrenheit is left in a room that is at 65 degrees Fahrenheit and begins to cool. Temperature readings are taken each hour and are given at the table below. In this scenario, the temperature is a function of the number of hours. So if I'm looking at that, even the notation kind of helps determine what's going on. Capital T, that's your function. That's almost like that f of x, okay? And the h is your x value. So I can almost think of this as like my y and my x. Okay, my dependent, my independent. I'm plugging this value into the big function. Okay, so this is what the chart gives us. At 0 hours, the temperature is 212. At 1 hours, the temperature is 141. 2 hours, it's 104, and so on. So it's saying evaluate T of 2 and T of 6. In other words, it's like saying what happens to the temperature at 2 hours. So when H is equal to 2, that's another way to look at it. So when H is equal to 2, the temperature is 104. Okay. At the time value of 6 hours, I want the temperature. So the temperature at 6 hours, if I look over here on the chart, is going to get me a total of 68 degrees. Okay, so now I have to read this a little differently because it says for what value of H. So I don't know what H is, I need to know what it is. I'm looking at that, I already have the answer. So I know my answer here is 76, that output value. So I have to now go down here to my chart and say, I know what this is. What was the H value that produced 76? So the H value that produced 76 is 4. And then between what 2 consecutive hours will the final temperature be 100? Notice we're looking for H. What hours will the final temperature be 100? And notice what they're saying, between 2 numbers. So I'm trying to figure out, well, where would 100 fall? Where would that output of 100 be? So it would have to be somewhere in between here. So the two H values then would have to be somewhere in between 2 and 3. Okay. So for exercise 3, we have a function. I don't know what the graph is. I don't need to know what the equation is, but I have the picture of it, so I can actually see it on the right-hand side. And we're going to answer our questions based off of this graph. So now again, different way to notate it. I don't have an equation that I can actually just go right and evaluate it, but I do have a function I can read off of. So I'm going to evaluate the function at -1. Keep in mind what this is saying. I'm inputting a -1. I want to know what my output is. My inputs are like my x values. So this is like saying when x is equal to -1, what is the function going to be? So if I read over here at -1, I get my function to equal 0. Okay, when x is -1, the y value that corresponds to it would be 0. Okay, we'll try it again. I want to know what the function value is going to be when x is 1. So when x is 1, I have to read up to find my function. Here's my function. The function is going to be 4. When x is 1, y is 4. It's a different way to kind of read this. Your function at 5. So when x is 5, what is the y value? When x is 5, what's the output? So 1, 2, 3, 4, here's 5. I have to go down to read the output value, and the output then is -4. Okay. We're going to evaluate the function at 0. Okay, when x is 0. So if x is 0, and I'm going to go up 1, 2, 3, I get the output is going to be 3. So the function evaluated at 0 is equal to 3. And what special feature is that would always correspond to this? This is what's called your y-intercept. It crosses the y-axis. I think intercept sounds like intersect. So my y-intercept is always going to be when x is 0. Okay. So what values of x solve the equation f of x equals 0? So now this is different from what we just did. This is not saying x is 0, it's saying the function is 0. In other words, y is 0. Okay, so if the y value is 0, well, where is y 0? Think, so if I'm going up or down on the y-axis, that's where my y values change. So y is 0 anywhere along this line. So I would have a value here that would give me y is 0, a value here y is 0, value here y is 0. Okay, so I found 3 values. I found when x is equal to -1, when x was equal to 3, and when x is equal to 7. And f of x, anytime they're asking you this, if they're saying when is f of x equal to 0, that's a different way to say what is the x-intercept. Okay, I want the function to equal 0. I want y to equal 0. The only time y equals 0 is if it crosses the x-axis. And then it says between what two consecutive integers is the largest solution to f of x equaling 3? So the function equals 3. The y value is 3. So I'm going to go up on the y-axis 1, 2, 3. So f of x equals 3 would be anywhere on that horizontal line, and they want the largest solution. So my largest solution, I'd have to read over to the right-hand side, and I am looking at somewhere here. And they're saying, well, what are those two consecutive integers? Well, it looks like this would be at x equals 7 and x equals 8. So I could say somewhere between 7 and 8. So for number 4, so it says for a function, y is equal to g of x. It is known that g of -2 equals 7. So when I evaluate the g function at -2, when my input's -2, I get 7 out. Which of the following points must lie on the graph of g of x? So I plug in 2. So 2 is like my x value. I get out 7. 7 is like my y value. So if I plug in -2, I get out 7. So that's a great way to be able to make coordinates if you know that notation. Very easy to kind of put it into a coordinate style. Okay, and this last one, we are going to use our calculator, and we are going to take a look at this. So we have physics students drop a ball from a top of a 50-foot high building and model its height as a function of time with this equation. It says use your calculator to determine to the nearest tenth of a second when the ball hits the ground. And we're going to explain how we used our calculator to find the solution. So I've already gone into my calculator and I have graphed this function. Now notice I changed the window. Okay, I changed the window because I wanted to make sure I could see the entire graph first off. And if you're thinking about this, when you have physics students dropping a ball from a top of a 50-foot high building, I want to see this entire graph of the ball being dropped. Okay, so this is where they're starting to drop it and the ball goes all the way down to the ground. Now we have to think about, well, what's going on with the negative side? Well, really and truly, this isn't happening. It's not as though the ball is getting launched up into the air before the person stands up at the top of the building and drops it down. So really and truly, the only part of the graph that I need is this positive side of the graph. I don't even need this. So I could even shrink my window up a little bit more so that I don't see that. So I'm going to go window, zoom, settings, and I'm now going to change my X minimum, and maybe I just give myself just a little bit of room, and I'm going to say okay. Okay, so that's my minimum. Do I even need all of this over here? Nope, not really. I could change that to, again, give myself a better window, and I don't need it out to 10. Maybe I only make it out to about 5. Okay, sometimes you just got to play around with it until you get the window to be where you'd like it to be. So here's our function. And we are going to use our calculator to determine to the nearest tenth of a second when the ball hits the ground. Okay, well, if the ball starts up here, think of this, it's almost like modeling the path that the ball is going in. The ball is going to hit the ground down here. Okay, and I know that because when the ball hits the ground, it's not moving anymore. Okay, it's modeling its height as a function of time. There should be no more height happening if it hits the ground. So what I need to do is I want to evaluate this location. Okay, if we go into menu, we do analyze graph, I want to find what's called the 0. Okay. And again, notice these questions, lower bound, upper bound. So I want to go to the left of where I think it's going to hit, which is there. So I'm going to go to the left, anywhere to the left, anywhere to the right. And now notice I get this value. And they're asking us to round to the nearest tenth of a second. So nearest tenth, if I were to round this up, that would give me 1.78 for my value of when the ball would hit the ground. And you would explain that. So on your notes where it says, explain this process, explain how you used your calculator to find the solution, you could explain to me, I went to my graph, I went to the menu option, I got the 0, went to the left, went to the right, and got my value. Okay, that's not the only way. You could get a table, but notice how weird this value is. And by weird, I mean there's decimals. It's going to take a while for you to zone in if you were to just use your calculator. You'd have to keep changing the table settings. So this 0 button is way easier than using your tables. Okay, so that's a little bit with our functions and our notations. We will practice this a little bit more in class. Come to class with any questions that you have, and I will help answer them for you. Hope you guys have a great day.